All right, guys, hello again. Let us look at a couple things here. Let's look at topic 11. Let's look at problem number 62 and what they're trying to say here with that. For problem 62, number 62, a class, topic 11 now, 62. A class of 10 students taking an exam has a power output per student of 200 watts. Assume the initial temperature of the room is 20 degrees Celsius. And that its dimensions are 6 meters by 15 meters by 3 meters. What is the temperature of the room at the end of 1 hour if all of the energy remains in the air? If all the energy remains in the air in the room and none is added by an outside source. The specific heat of air is this, and its density is about that. So the specific heat of air, let's just write a couple things down here, guys. It should go pretty smooth. There's 10 students taking an exam together. Let's say a lot of stuff here. The specific heat of air, we'll just call it C, is 837 joules per kilogram per degree Celsius. So it's per kilogram per degree Celsius, and there we got that. The density of air, rho of air, rho in this case, doesn't really, not a big deal here. Rho of air is about 1.29 times 10 to the negative 3. It's actually 1.29 kilograms per cubic meter, but this is, well, let's talk. I mean, they did, let's play the way they want to play. Times 10 to the negative 3 grams per cubic centimeter. There's a lot being said here. The kids, a class of 10 students taking an exam has a power output per student of about 200 watts. Power output of 200 watts. So the total power is 10 students, each one having a power output of 200 watts. The power, 10 times, 10 students, each one with a power output of 200 watts, that's 2,000 watts. That's going on there. It's pretty impressive. Well, let's see how impressive that actually is. Well, if that's the power output, the total amount of energy per unit time is the power output. It's this. So if you want to find out how much energy, how much work is being done, or how much energy is outputted, it'd be P times T. If that's the case, using different things here, I have to mess up my finger, guys. I need something work this thing out. They're saying 2,000 watts, that's 2,000 joules per second, and they're in there for 1 hour. For 1 hour, huh? 1 hour, there's 60 minutes in an hour. 1 hour has 60 minutes, and each minute's got 60 seconds. There's 3,600 seconds. So the total amount of heat energy that they put in there, the total amount of energy, heat energy, Q would be heat, in this case heat, but somewhere else I could say work in some other regard, using conservation of energy considerations. You've got 2,000 times 3,600, that's 7.2 times 10 to the 6th. 7,200,000 joules. 7,200,000 joules for that to happen. 7,200,000 joules if you allowed the students to be in there for an hour. That's how much so they're going to heat up the room. So they did this, and just trying to figure out now what's going on here. Well, if this is what's going on, let's find out how much mass of air is actually present. Are you guys all right with let's see what else I can say here. We know that the row of air equals the mass of air divided by the volume of air. Okay? Sounds good to me. I want to talk to you a little bit about that. Now we're using what they said. I'm not too thrilled by it. At one point, we already know that the row of air is 1.29 kilograms per cubic meter. The way I can prove it to you is this. If you multiply, if you wanted to convert, if you multiplied this bottom thing by a million times 1 cubic centimeter. There's a number of ways you can do it. Let me try to give you more of a gut feeling here for what's happening. If you multiplied top and bottom of this ratio by a special 1 called 10 to the 6th. You multiply top and bottom of this ratio rate, this thing right here, you multiply it by a special 1 called 10 to the 6th over 10 to the 6th. A million over a million. A million times 1 cubic centimeter. A million cubic centimeters is 1 cubic meter. A million times 10 to the negative 3 is 10 to the positive 3. 1.3 times 10 to the positive 3 is 1,300 grams. 1,300 grams is 1.3 kilograms per cubic meter. If you want to use the more accurate one, 1.29 kilograms per cubic meter, go ahead and do so. Tell you what I'm going to do. They told us that the volume, they didn't tell us the volume. They said length times width times height. And that's equal to what? Well, in this case, they told us it was 6 by 15 by 3. 6 by 15 by 3. These are all meters, guys. These are all meters. So they're saying, you see here, 6 by 15 by 3. This times this times this. Let's see what we got here. This is 90 times 3, 270 cubic meters. That's the volume. If that's the volume, let's find, that's the volume, let's find the mass. Isn't the mass rho times V? Isn't rho 1.3 kilograms per cubic meter? Isn't the volume of the space the students are occupying of all the times to be wearing a bandage on my finger? I mean, it's right when I'm trying to finish this thing. Unreal. Anyway, is that legible? Can you see that okay? If you can see it, they can see it. All right. That's 270. M equals rho times V equals 1.3 times 270. Let's talk. I mean, it's going to be 81, it's going to be 351. Somewhere in that ballpark. 351 kilograms. That's a lot. That's a lot of mass. You wouldn't think air would have that much mass. I mean, that's pretty crazy in its own right, isn't it? But let's see, let's just confirm it. That's 270 multiplied by 0.3. That is 1 times 270 and then 0.3 times 270. Yeah, it's looking good to me, guys. Like it's right on the mark. So it's this bit, that's the mass of the air in the room. It's the mass of the air in the room. And yeah, that may be the mass of the air in the room. And this is how much, and that's how much energy is there. So we got to figure this out. I mean, it's not too bad here. What we're saying here is, what's the change in temperature? And I think what they were saying, if they're trying to ask us something like that. Let me see here. What is the temperature of the room at the end of that? So the room started at 20 degrees Celsius. Started at 20 degrees Celsius. Well, let me see here, guys. Look at all this. Is it true that all that heat, how does that all work? Cm delta T. Cm delta T is going to make it happen. I'm going to find out the change in temperature, and I'm good. Remember, the initial temperature is 20 degrees Celsius. If it's a subtraction or addition, it's okay to use Celsius. If you're using ratios, you must use Kelvin. You must use Kelvin. There's more that can be said about this, but I don't think we're in the mood to be talking more about that stuff, man. We're kind of pressed for the time. If you're doing a ratio, you've got to be using kelvins. Any kind of ratio, any kind of multiplicative or division, if there's division or multiplication, some kind of ratio going to be happening, you're using kelvins. If you're going to get a temperature difference, that's more of an addition and subtraction sort of phenomenon. This is what you initially got. Let's find out what delta T is. See, these guys, what's going to be the final temperature for these guys? It's going to be the initial temperature plus delta T. That's what they're going to have. It's going to be the initial temperature, 20 degrees Celsius, plus the delta T that we got in there. We'll put that, we'll have that right here. We'll have that right here. The TF is going to be right here. We know what it's going to be. We're going to figure it out. We're just going to add the delta. Let's find what the delta T is. Delta T equals Q over C times M. Delta T equals Q, and this is the amount of heat that went in there from the kids, from the students, kids, adults, who knows? I mean, but that's what went in there. 7.2 times 10 to the 6 joules. That's legible? You can see that okay? You're seeing it all right? Okay, it's okay. All right. Again, this is my wrap here is kind of hitting everything I write, so it's smudging everything sort of. But as long as Christian can see it, I know you guys can see it. We're getting filmed here. We got this. C. We were told C is 837. Joules per kilogram degrees Celsius. 837 joules per kilogram degrees Celsius. The kilograms are going to cancel with the kilograms in there. 351 kilograms, 837 joules per kilogram degrees Celsius. The kilograms cancel. Joules and joules cancel. Per degree Celsius, the degree Celsius band pops up this way, and you're there. This is a great problem. It's not really that hard. It's easier for you to do it than for me to explain it, but it's quite tedious, but let's see what we got. You are going to multiply these two and put it into here and see what happens. Okay, so if that's the case, $24.5 or thereabouts, right? 24.5 degrees Celsius is the temperature change. The temperature changed by 24.5 degrees Celsius. You started at 20 degrees Celsius, it changed by 24.5 degrees Celsius. And there it is. The end of the day on that one. I mean, when you look at that one, TF is the 20 plus the 24.5. That is horrible. All right, let's see. Plus the 24.5. Plus 24.5, that's 44.5 degrees Celsius. Final answer. You guys okay? I hope you're okay with that, guys. I mean, we're looking as how this thing is. Okay, that was 62. Let's go to 63. 63, they talk about a bar of gold, AU, is in thermal contact with a bar of silver, AG, of the same length and area. One end of the compound bar is maintained at 80 degrees Celsius, and the other end is at 30 degrees Celsius. Find the temperature at the junction when the energy flow reaches a steady state. So somehow together, these guys are going to flow and see here. So we're talking about how things, the transfer of energy from one place to another. Now there's three kinds of transfer of heat energy. There is conduction, which is what this is. There is conduction, convection, and radiation. Conduction is when things are right next to each other and there's two bars, there's a bar of gold and a bar of silver next to each other. One's being held, one end of the gold bar is being held at a temperature of 80 degrees Celsius, and the other, where the silver is, let's say, is being held at 30 degrees Celsius. There will be a flow of heat that way via conduction. They're going to hit each other, the molecules inside are going to hit each other, and there's going to be conduction of heat regarding something like that. That's conduction. Convection is when a whole large air mass from Canada moves down here and makes us cooler on a hot summer day or something like that. That's convection. Radiation is associated with electromagnetic radiation that comes from a body that's been heated. If it's heated up, it'll give off electromagnetic radiation, which will also heat the environment. And for that to transfer, it doesn't even need air or anything else present, like conduction and convection do. So it's conduction, convection, and radiation. Look at that in the book as well, guys. We're talking about that. All right, let's see what we can say. Let's talk about problem 63. And this is a classic conduction problem. Well, I'll tell you something. It's easier for conduction to take place if there's a lot of area that is exposed on each, if there's a lot of area in contact with something else, the rate at which heat is transferred is greater when there's a lot of area in contact with the place to where you want to transfer it. Also, if the length of the item is shorter, it's easier for the conduction of heat to take place compared to if the bar is longer, it's harder for the conduction to take place. So big area exposure means easier way for conduction to take place. Short length makes it easier also. So a small area and a long length, wow, that's going to make it really difficult for the conduction to take place. Also, the bigger the temperature difference between two places, yeah, that really is amiable to conduction taking place. So there's a lot that can be said here, guys. I don't know if I'm running out of chalk here that I can use. So for 63, when two things are in contact, the way they showed it in the book, they wrote it like this. You know, there was the gold, and there was the silver. Just try to make it look a little different. Here's the gold. Here's the silver. It's being held at a temperature of 80 degrees Celsius here, and this is being held at a temperature of 30 degrees Celsius here. Heat flows from high temperature to low temperature. See what I can do. There's the silver. And there's the gold, let's say. Okay. So they're saying something like this. When there's an equilibrium temperature, things should go pretty smoothly. Now let's talk a bit. We talked about the rate of, I already I said it, I hope it made a little bit of sense. Power is flow of heat per unit, amount of heat per unit time, that's power. And that's equal to some constant times the area of exposure times delta T divided by the length here. This is a lot easier than it looks. Again, it'd be a lot easier if we were all here together in person, guys. It's what it is. But we're talking about a situation. K is a constant. The rate at which energy is transferred, that's heat energy per unit time, it's called power. The time rate of change of energy transfer, called power, heat per unit time, is dependent upon a constant, depends upon the item under consideration, the material, also directly proportional upon the area. If the area is very big, if the area here is very big, and the area here is also very big, then there's more heat being transferred across that big area. If there's a big delta T, what does that mean? Here's TA, here's TB, whatever. TA minus TB, 80 minus 30, 50. The bigger that is, the more energy transfer. The shorter this is, the shorter this thing is, L, the easier it's going to be for there to be transfer of heat. The easier it's going to be for there to be, the shorter it is. The longer it is, it's going to hamper it. So I'll tell you what I'm going to do. There is, we said this about P. We're going to say that the power, now the way out, our way out of this thing is a bar of gold AU is in thermal contact with a bar of silver of the same length and area. Okay, so L and A are the same. One end of the compound bar is maintained at 80 degrees Celsius and the opposite end at 30 degrees Celsius. Find the temperature at the junction when the energy flow reaches a steady state. In other words, the energy that's flowing here is equal to the energy that flows into this junction right here is equal to the energy that's flowing out of that junction right there. So let's see exactly what we could say here. I guess they're trying to say here, I guess what they're trying to say is find the temperature at the junction for there to be energy flow that reaches a steady state. There's going to be a temperature right here at the junction, you guys. Temperature right there at the junction. I'm going to make this thing work. I'll tell you what. The power on the gold side is going to equal the power on the silver side. What does that mean? That means that K, there's a K associated with gold, KAU. Area is A, and at 80 degrees, it's going to flow to the junction, and the junction's got to be at a lower temperature. It won't flow there if it's not. Guys, heat always flows from hot to cold. it flows from high temperature to low temperature. So it's got to be that. Over L. KAG, silver, area is A. The junction's got to be hotter than silver's cold side. Remember, this is the thing that was the ticket. And now we're setting them up that way, and this is the way to go here. Christian, is that legible? It's okay? Okay. Okay, you think so, guys? Think you're all right? Let's multiply by big L on each side. Multiply by big L on each side, and that cancels. Divide by big A on each side, that cancels. I want to remind you, I don't even know that any of us even knew it, including myself, but 314 and the appropriate units for the K for AU and the K for AG is 427. That's a real good conductor of heat. All right, so we got that. Well, you do the whole song and dance, guys. You got to remember what these are. We'll throw them in there when we got to. Again, what did I do? I multiplied by big L on each side. I multiplied by big L on each side. The L's cancel. I divided by big A on each side. And before you know it, you've got this. And the other one's K. Yeah, it's pretty good. Put in the right units, I guess. 314 is KAU. That's for the junction. KAG is 417. 427, rather, I'm sorry. The other one is TJ. That's good. Christian, is that visible? Pretty good? It looks good? Okay. So we got this. Let me see what we can do. The rest is math, guys. You're going to do all the mathematics to solve this. I mean, that's the hardest part of this whole thing, guys. The hardest part of this whole thing is right here. It ain't, well, I mean, there's a lot of challenging parts to it, but this one right here, you're just going to say 314, 80 minus T sub j. That's the only variable. This is 427. Solve for T sub j. Well, you're going to wheel and deal. You're going to do all the stuff you got to do there to get it. And it's okay. I mean, we got it to here. It's not okay. I can't find any chalk. I mean, I can actually use. Let me see here. .2, that's visible, right? We're looking good, okay. 51.2 degrees Celsius for that. And that gets us there. And that's topic 11. At least topic 11 that I wanted to say something. If you really want to look at topic 11, look at everything I've solved, you guys. And I prefer you do that. Read the chapters. I'm sorry you're getting thrown into something like this. Not your fault. Not my fault either. Nobody's fault. I mean, it's happened. But read the chapters and look at the stuff I've given to you. You can do this as a self-study. People up to this point, about 90% of the class has been doing this as a self-study. So there's nothing wrong with that. I mean, I purposely designed it as such. So that's topic 11. That's out of there. Let's go to topic 12.